Hi, and welcome to another Earth Science Classroom video. We're looking at paleomagnetism, number 2. The video 1 was looking at the discovery made by Hess in 1963, looking at the convection currents for the ridge and the spreading center and the fissures in the mid-ocean ridge, allowing lava to come up from uprising magma in convection currents, producing lava flows, basaltic lava flows that would cool and form basalt. And you saw the age of the rocks would differ the further away you get from the ridge. And then literally straight after that was published, or even before it was published, just the notion of hearing about this theory, we had Vine and Matthews in England work on the magnetism and the polarity shown in the rocks, in the basaltic rocks, by the magnetite crystals that were mostly made of iron oxides. They were magnetic and they would point in a certain direction according to the current polarity of the Earth, the magnetic field. And then we had another guy named Morley, Canadian chap, in a year after, who also found the same things. So they found that inside this basaltic rock, which makes up the majority of the ocean crust, deeper down under the sedimentary rocks, they were magnetic, all right, because of this mineral magnetite that was made of iron oxide elements, and it showed the polarity. And the polarity is like a big bar magnet. So you have on one end, you have the north and other, so it's a dipole magnet. And the Earth kind of resembles that. So that was a recap on the first video. This second video, we're going to look at the application. The application, what did Vine and Matthews and Morley really do with that information? And look at the signature strips that were on the ocean floor and what that meant as well. So the application of this knowledge of magnetism in the rocks and the fact that the basaltic rock, as it cools, it forms like a time stamp of the current magnetic field in which way it's pointing. Now I'm saying that because when they used magnetometers all over the Pacific and the Atlantic Ocean. Let's erase that a little bit. Atlantic, there we go. And what they found was they took the ocean floor and they found this really cool bit of evidence. So I'm just going to draw a sea floor here, and here's my ridge. All right, so there's the ridge, there's the fissures where the lava comes up. Okay, and we have these very tall undersea ridges and mountain ranges, continuous all the way through the mid-ocean ridges, all through Atlantic, Pacific, Indian, Southern. Okay, and we have the crust here, the ocean crust, and below it we have the convection currents. So CC for convection currents. Now, after Hess realized the age of the rocks and basalt and the ridge and lava and the seafloor, they're moving basically with the convection currents. Then, with the magnetometers, they found that by the ridge, the rocks that were young, brand new, newly formed, brand new, they had a certain polarity of magnetism. So the magnetite was all pointing this way. And as they went across the ocean floor, they would find a weaker band smaller, weaker band like this. And they found it on the other side of the ridge. So it's the same weaker magnetic signature or field on the other side of the ridge. Now, this seemed to be symmetrical. And they did more tests, more experiments, more discoveries, more of the ocean floor. And as they got further away, they would find these alternating bands. They weren't perfectly symmetrical, but they were pretty much, you know, these alternating bands where the polarity that was kind of fixed into the basaltic rock as it cooled. Don't forget, the age of the basalt increases as we go away from the ridge. So you would think that there would be just like all the same polarity, all the same age of rock, because it's moving, because the age of the rock shows it's moving, and this polarity signature, this stamped in signature of polarity inside the basaltic rock through the magnetite crystals, they're indicating these directions of the current and ancient, or paleo. Don't forget, this word paleo means ancient. The ancient magnetic fields and their polarity, their direction, which way is north, basically a little compass. So these rocks act like little compasses, and they're showing the scientists which way north pointed at that point in time in Earth's history. So the smaller, weaker, less intense bands or strips parallel to each other that were smaller, these blue ones, the polarity was the other direction, the complete opposite direction. So there's a 180-degree change. The thicker ones, the more intense ones, were pointing north as regular, and these weaker ones were pointing the other direction. So in terms of application, we can look at the discovery of parallel, symmetrical stripes of magnetic polarity on the ocean floor. Ah. On the ocean floor. And what is that showing? That is showing that there are changes to the Earth's polarity and intensity of that magnetic field over time. It's not continuous, it's not consistent, it is always changing. And if we look over here, I draw an Earth. All right, here's my Earth, very crude, okay? So what happens is, when I say polarity, I'm talking about a dipole magnet. Di means two, pole means, obviously, polarity. So two poles. There is a north and a south, okay? Like a bar magnet. And what happens is, we know this is formed in the outer core through the liquid iron alloy moving around, and it aligns the electrons and causes a magnetic field within the iron. So if we have our, let's say, our purple, so looking at the purple strips, okay, the purple strips that were facing north. So north on a compass, as we would find today. Take your compass or your cell phone, and you look where north is. That will give you the same as these strips closest to the ridge. So we're in currently a normal, with a normal polarity. So what does it look like? So normal looks like this. So you have the magnetic fields, I'll use green, okay, all right, coming in, leaving the South Pole and coming in at the North Pole, leaving the South Pole, coming in. And these would also be smaller by the equator, and they get larger as you increase with latitude. And this would be all around the Earth. Okay, so, and here's my equator. And we know that the axis of the magnetic field is about 11 degrees off the tilt. It's 11 degrees off. So magnetic north is not exactly the same place as geographic north on a map. And we'll find in a different video, in a future video, that the poles, actually the North Pole in particular, has what we call wandered around. It has taken a trip around certain areas in the northern hemisphere, high latitudes around the Arctic, Greenland, North America, and Europe. And we'll get to that in a different video. But it's basically 11-degree inclination, right, off the regular axis of the tilt of the Earth. And we have a normal polarity where the North Pole, the compass is pointing north, and polarity looks like this. So wherever the compass or the magnetite is pointing, direction it's pointing, here we call magnetic north. Now it gets a little tricky because in magnets, the opposites attract. So when you actually have a compass out in your hand and compass is pointing north in a certain direction, really, in real time, your compass is really pointing to the South Pole, the South magnetic pole, because opposites attract. The North magnetic pole up here, the North Pole here, really is a South Pole, so it's attracting. It's attracting. Here's the South, but magnetic South, because it's being attracted towards the South. And then the North, it is being repelled away. See, it's going away. So repulsion and attraction. So really, when you're pointing the compass north, you're really seeing the attraction of magnetism to opposite. So if it's North Pole, magnetic north, looking at the south part of the magnet. And this is also true when we look at a reversal of polarity. Now, in a reversal or reverse polarity, as seen on the stripes that are parallel and symmetrical on the ocean floor, it's a weaker intensity of magnetic field. And it switches, it's a 180-degree switch between normal and reverse. So if the normal polarity is pointing towards geographic north and magnetic north, then the opposite would be the case for a reverse polarity. And your compass would point in this direction, towards the geographic South Pole or the Antarctic continent. So basically, there's a reversal. So if it was coming in at the North Pole, geographically for normal, it'll be going away. So I was going to draw it going away and coming in at the south. In and there. So these little smaller ones at the equator and mid latitudes, same thing. Small ones here and big ones here. So you have this switch, this reversal of 180 degrees, where the Earth's magnetic field switches, and for the last 2 million years, well, actually no, for the last 3.6 million years, there's been 9 major reversals in our Earth's magnetic field. And each 1 million years of continuous polarity is called a chrone. So we can basically divide time into chrones, which show consistent polarity over a given time. This is usually 1 million years. Now we've been recently in a period of a long time of normal polarity, but in the past it has switched and it will switch in the future. Now this is again where your compass is pointing north, going this way. So I'm just going to change this to south and put in north in your compass. So compass north. So really this will be the south part of the bar magnet, and this will be the north part of the bar magnet as well, because opposites attract. Now, this has been known to fluctuate every 200,000 years to 400,000 years. That has also changed over time, but recently it's in that kind of pattern, and we are kind of on the brink of a potential reversal, but nothing changes except for the magnetic field. The field of magnetism, that changes. The geographic locations do not change. Perhaps the birds that use the long-range navigation through charged ions in their brain through the magnetic field, we messed up, so they fly north for the winter rather than south. They get messed up, but I'm sure they'll figure it out. All right, so that is reversal of polarity, the application, and we'll also get on to looking at the polar wandering, or the North Pole polarity wandering over time in the next video, guys. Hope you enjoyed this, and please subscribe if you would like to see more videos.